Okay.
All right, so I'd like to take a look, or just make a discussion about number 9 and then number 17. Now, on another thing, another small little point I want to make about number 11. Number 11 said to minimize x cubed plus y. And a lot of people get confused on that one because they don't give it a name. You should write f equals x cubed plus y, right? And then, because it's like x cubed plus y, but what am I calling it? How do I do the derivative, whatever? They didn't give it a name. Give it a name. F equals x cubed plus y, and then go from there. All right. So I want to look at number 9. I want to contrast that with number 17. And then, so you can see in our steps here, our 7 steps, how it's same process. One, though, is a very kind of basic, easy problem. And then what makes the other one, oh, no, I did it again. Okay. There we go. Can I undo more than one step? Yeah. Okay. New page. There we go. All right. So how we can contrast how they're kind of similar, but where things are different. All right, so number 9 says, and again, this couldn't be much simpler. If I ignore the first sentence where it compares back to example 4 and talks about implicit differentiation, and I'll show that at a later time, how you don't always have to get it in terms of one variable. You could do implicit differentiation. Most of the time, that's not a good plan. All right. It's more difficult going that direction, but so that's what they did. So let's go back to that example 4. And it says, I think, hopefully you read that. It says 2 non-negative numbers that add up to 10. What's the largest their product can be? Right? So thankfully, in number 9, they actually set it up, did the labeling for you and everything. They said, well, that means x plus y is going to equal 10. And we need to identify the product. The thing we're trying to maximize is product. And so they even gave us a nice equation for it in number 9. So they've done steps 1 and almost step 3, right? I mean, they've identified for us what we're trying to maximize, which is product. They've given us additional information, write and label like I had up there. So we use x and y, and then the next step is to do what? Get it in terms of one variable. So we go to this, we substitute it in, we get p equals x times 10 minus x. I mean, this couldn't be much simpler as far as a problem to set up. As these go, I mean, as optimization problems go, this is the easiest kind there is right here. I suppose easier would be if they just gave you a function with one variable to start with. That might be a little easier yet. Okay? Actually, we'll have a few of those in today's homework, some business applications. So that's even nicer. But there we are. We're down to step 3 in that list. We've got the quantity to be optimized in terms of one variable, right? So we're ready to go on to step 4. Now, what I wrote up there in step 4 was what? Find critical points, right? Critical points are what? Okay, but so derivative is 0 or undefined. So let's do derivative 0 first. But instead of writing 2 things, I just wrote critical points in that list. So that tells me I got to do derivatives. So critical points, derivative is 0. That's going to be when x is 5. Okay? P prime undefined? Question mark? Never. I mean, P prime is just a linear equation. It's never undefined. About the only time it's going to be undefined is when when you have a fraction and the bottom is 0. That's the most common time a derivative is undefined. So a lot of times the answer to this is never. Okay? The next step on that list was discuss endpoints or end behavior. Endpoints come from your inputs. Okay, it comes from this equation in step 3. Look at the inputs. What's the littlest input we can plug in? What's the biggest input we can plug in? Now, sometimes you go back to your secondary info for that. What's the biggest or littlest x we can put in? 0. And the biggest x would be 10, because they said they're not negative, right? So x and y can't be negative, so to add up to 10, That's the biggest and the littlest you could be. So this is a nice list of candidates problem. All right, this one sets up very nicely. So I would put what for my list of candidates here? P of 0, P of 5, P of 10. Which of course tells me where to plug it in. If I've written it properly, I put the 0 in, I get 0. I put a 5 in, I get 50 minus 25. And I put a 10 in, I get 100 minus 100, which is 0. Then it said there needed, this is that step where that is my justification. My list of candidates is my justification. So I answer the question that's asked. It said, what's the largest the product could be? Well, that's it right there, 25. It doesn't hurt. It's probably a good idea. These are story-type problems. To end your answer, to end the problem with a sentence. In other words, take all this. This is all good. And this is all worth points as you go through it. But now finish it and say the maximum the product could be is 25. You know, and put a box around that, and that's kind of your final answer. If I just saw this work here, don't count on the person grading it deciphering all your work and deciding what you want your answer to be to the question. Okay? A final sentence that declares that is really what you should probably have at that point. So let's look at number 17. But that's, if you go back to the list, okay, and the steps, that's pretty much right down the line. The first three were very easy, and that's what distinguishes a pretty easy one of these problems with one not so easy. If you can get your equation in terms of one variable and so forth, and get down to step 4 very quickly, that's a pretty easy problem. Okay? All right. Now we come back here to the Shanghai problem, which will live in infamy because I will mention the Shanghai problem often during the year. Okay? As a strategy. So didn't expect probably anybody to come up with it on their own this time around. But going forward, we should. All right. So what do we got? Well, we got this parabola. And they talk about how the parabola fits snugly inside of an isosceles triangle. Which means that the sides of it are what? Tangent. So hopefully, at least, if nothing else, that triggered a thought of a derivative. Because that's what a tangent line, the slope of a tangent line is the derivative. We've done equations of tangent lines with a point and a slope. Now, what's different about this problem is our normal tangent line problems we've had. We're given a function, and we're told the point on the function where we have the tangent line, right? Say at x equals 7. Well, what do? We do the derivative. We plug in a 7. There's our slope. What's different about this one is we know the function, and we know there's a point where it's tangent, but we don't know what that point is. But what's the additional information we have in this one that we don't normally have is we have some other points on that line. Normally we have a tangent line to a curve. The only point on the line we know is the point where it touches a curve. Remember, that was the whole problem with doing slope, is we didn't have 2 points to do slope. So that's where the derivative came in handy. We did the derivative, plugged in that point, and they gave us our slope. Well, now we will potentially be able to use 2 points to do slope, and that'll be the secret to the Shanghai problem. Okay? All right. So, anyway, we got this scenario here. Let's get back to our optimization idea. Step 1, identify what we're trying to optimize. What is it? Area. Area. Now, I've got a picture of this. This is the situation right here. What they're saying is somewhere along here, there's a point where that triangle has the littlest area possible. Up here, now it's pretty easy to see that area is getting bigger and bigger and bigger. Getting smaller, smaller, and now at some point it starts getting bigger and bigger again. Somewhere in here, that area is a minimum. Okay? So, this just helps us maybe a little bit to see or understand the situation. So, identify the quantity area. Write and label an equation of that quantity. Now, I might have also said here to draw a picture too, to help that in step 2. All right, so area to be minimized, or excuse me, quantity to be minimized is area. All right? Now, what's wrong with that? 2 variables. Okay? So, notice in step 2 I had said something about labeling. Why did I pick B and H? Well, that's area of a triangle. So somehow I better get B and H in my picture. Okay? So, where would H be in that picture? This point right here, right? That would be the point 0H, right? That'd be the height of the triangle. Where would B get involved? That'd be the distance between here and here, right? Would be B. So what would the coordinates of that point be? So now over here, this would be negative 1/2 B and 0. But do you notice on my picture there a minute ago when I slide this point, this one changes too? So we really can ignore this half of the picture. We really only need to work with this half over here, okay? All right, so I'm going to call that 1/2 B and 0. So that gets that involved. Now, since we have 2 variables, and notice, you can already tell what's difficult about this compared to this is we got to the 3rd step very easily. We got down to our equation with 1 variable very easily. Here, it's a lot more difficult to get to that point. That's where the difficulty lies. So we're trying to get this in terms of 1 variable. So your first thought might be, if I can get an equation that has B and H both in it, I can solve for B and then substitute it in. That's typically what you want to do, just like this. Here's my equation. It's got 2 variables. If I had one equation that had both X and Y in it, I could solve it for one of them, substitute it in. That's what I'd like to do. So I need an equation that's got B and H in it. The only thing I can think of that would involve B and H right now would be to do a slope calculation between those 2. So I could subtract the Y's, and I could subtract the X's. Now, I'll just tell you, it turns out that's not going to get me anywhere right now. But you know what? Who knows? When you don't know what to do something. When you don't know what to do something. You might trigger something. You know, it might think of something. Now, the problem is I need an equation, so I need that equal to something. Well, it does equal what we said a minute ago. What's another way to say the slope of the tangent line? The derivative of the parabola. The derivative of the parabola is the slope of that tangent line. So it would equal negative 2x. Now, the only problem is I've introduced another variable. So it turns out that this is not going to really get me anywhere, but that idea is. And that is the secret to the Shanghai problem. And this is what I want you to remember from here on out, is whenever I talk about use the Shanghai strategy, the Shanghai strategy is 2 different ways to write slope that are the same. One way is subtract the 2 points, do a slope formula. The other way is the derivative. Derivative, slope between 2 points, set those equal to each other. That's the Shanghai strategy. Now, unfortunately, it doesn't quite work here because we have the H and the B and the X. That's too many variables. The secret then becomes, in this one, is let's name that point. What can we call that point? XY. Because by definition, XY are the points that are on the parabola. Now that gives me another variable, Y. I'm going to get the Y out of there because what's Y equal to? Y is the same as 1 minus x squared. Right? Y is equal to 1 minus x squared. So instead of calling that Y, I'm going to call it 1 minus x squared. So that eliminates a variable, which is nice. Okay, now what can we do? Do the same thing we just did a minute ago, except let's pick those 2 points to do my slope. Okay? So we're going to go 1 minus x squared minus h on top, and we're going to do x minus 0 on the bottom. And we're going to set that equal to negative 2x. So the left side is one way to do the slope of that dashed line, and the right side, the derivative, is another way to do the slope of that dashed line, but they have to be the same because it's the same line. All right, now I go ahead and I multiply that over. And I get negative 2x squared. Let's see, we're trying to solve for h here probably, so I'm going to add the h over to this side. I'm going to add the 2x squared over to there. And I get h equals 1 plus x squared. Now what's that do for me? I could substitute that there, but then I still have a b in there. Let's do it again. Let's do it with these 2 points now. Let's do it with those 2 points. Let's go 1 minus x squared minus 0 over x minus 1/2 b, and that equals negative 2x. And so now when I multiply the bottom over to this side, I get what? Distribute that, that'd be negative 2x squared plus bx. So now add 2x squared over to there, I get 1 plus x squared equals bx. Divide by x, 1 plus x squared over x is b. And I'll now substitute that over there. So I've got a equals 1/2. In place of b, I put 1 plus x squared over x. In place of h, I put 1 plus x squared. Now I've gotten to step 3 on that list of steps. But man, you know. All right, but now that's a strategy that we know. I mean, that's something, and it's a common problem, really. I mean, on the AP test in the free response section, it seems like almost every year there's some sort of a problem with a tangent line at some unknown point, but we do know other points on the line. Now, they're not always as hard as this one, but that's really what the Shanghai problem is. You've got a curve you know, you've got a tangent line at some point you don't know, but you know some other points on the tangent line. So what you can do is you can do a slope between the 2 points on the line and make that equal the derivative. And that can eliminate one of the variables and help you to find the point that you're looking for. All right, so the Shanghai strategy. So now we're down to there, so now what's the next step? Critical points, right? Derivative. So do the derivative of that. And we're not going to take time to have you do it if you haven't yet already. I know some of you have that have come and talked to me. But so we do the derivative, we set it equal to 0. And you get x equals 0.577 something, and a negative, but that of course would be over on the other side. So you're going to do your derivative. Now again, don't be afraid to use a calculator here, right? This isn't that bad a one. You can rewrite it, do a quotient rule. It's not too bad. But again, on the test, when we do this test, time will be a factor, you know, and so don't be afraid to type this in to your calculator, let it do the derivative, then do the solve to set it equal to 0. Okay, critical point is also when a prime is undefined. When is this undefined? When x is 0. Okay, so you got an x in the bottom, so when x is 0. What about my endpoints? Here's my equation. X is my input. What's the littlest input I can have? Up here, the littlest x could be would be up there we talked about. Of course, it could go back on the other side, but then that's the other point over there. So we're only looking at this part. So 0, what's the biggest x could be? If the tangent line was all the way down there at the x-axis. So the endpoints are 0 and 1. So my list of candidates for this one. Would be A of 0, A of 0.577, A of 1. All right, let's go backwards with it. What's A of 1? 2. A of 0.577. 1.5396. A of 0. Undefined. Not only is A prime undefined when x is 0, but so is A. If you come back to the A equation, you put a 0 in, it's undefined. Well, remember, of course, that was an infinite, right? If it's 0, you got horizontal tangent line, it's no triangle. It's an infinite area. What I would do, though, is you should actually discuss that. You should discuss if this point was up here, the tangent line would be horizontal. So you should say something here. And you can't just say undefined. You should say something like area goes to infinity or something like that. Somehow discuss that when x is 0, that area is really, really large. Okay? You could get it from here too. As x gets really close to 0, the bottom's getting very small, the whole thing's going to infinity. So clearly the minimum area is right there. And then what did they ask for in the question? Did they want the minimum, smallest possible area? So there it is. If they wanted to know at what point it was the smallest possible area, then they'd be asking for the 0.577 number. Okay, so you have to answer the question that's put there. Yes, sir?
Wouldn't A of 0 not be a triangle anymore?
Right. It would, yeah. I mean, so, but it's area.
So if they were asking for the biggest area, what would you do?
They wouldn't ask that. It would be an infinite. I mean, there wouldn't be one, because what would happen is, the closer and closer you get to there, the closer and closer you get to horizontal. But it's not. It would hit the x-axis way out there somewhere, and you could always get just a little closer to the y-axis. So it essentially would be infinite. There would not be an x. Okay. All right.
Units? Do you just put units?
You can put square units, just say square units, or you could leave them off if they don't have units. Now, on the actual AP test, they're very, very careful to ask about it, the way they ask it for units. Get in a habit of always putting on units. Sometimes they actually give points for the proper units, and sometimes they don't. Okay? And we'll learn more about how you can kind of tell, but to be honest, you shouldn't even worry about it. You got enough to worry about when you're doing those problems. So you should just, you just get in a habit of doing it a certain way. Okay? And then you'll be fine. Okay. So let's jump right into the homework here today. I'm going to get you started a little bit. Again, I know that the getting you started is the hard part, and so we want to get ourselves to the point where we can do them without having to be given a start. But we're still in the learning process of it, so I'll help you a little bit here, and then we'll give you some work time. So the homework today is going to be, if you would look at that sheet, your homework sheet, it's going to be day 2. Now, day 2 talks about a few problems out of the book, and it talks about the business packet, and that's what this is here. Now, the business packet I give to you because many of you, if you're going to go into a business-related field like accounting or something like that, oftentimes the calculus class you take is an applied calculus or a calculus with business emphasis. And our book doesn't have a lot of business applications in it. So I've pulled this out of another book. So if you would look at page 216 in this little packet, there's this table on page 216 with some business terminology. Now, we won't worry about this term. Okay? We won't need to worry about that one. But let's go through a few of these. Now, you notice on day 2 on the assignment sheet, there's only a couple of problems in the business packet. Quite honestly, they're the easiest ones of all on the whole assignment. They're ones where the equation that you're trying to maximize or minimize is you've got one variable in it right from the start, and it's, they're just take a minute or two. They don't take very long at all. They're very, very basic ones. But we'll get into some more difficult ones as we go. But just getting familiar with the terminology. So typically in a business type application, we use a variable, often X, for the number of units produced or sold. So we're often talking about making some product and the cost of either producing it or selling. Most of the time we assume how many we make, we also sell. Okay, so we don't get into the situation of unused inventory or something like that, which would be a factor that we could bring in at some point, and you would in a college class and emphasize that. But a lot of the problems we just assume number we make, number we sell are the same. Little p, lowercase p, is normally used for the price per unit. And so therefore the revenue, the total revenue, revenue is a term, means the money you bring in, the money you get for selling your product would be just X times P. That's a pretty simple thing there. Cost, C, is the total cost of producing it. So you have the money you get in minus the money that you spent to make the thing. And then that's capital P, your profit. So profit is revenue minus cost, R minus C. Again, not something I think you need to memorize. It's just they're pretty common sense kind of things. Average cost per unit is a term that they use a lot. They put a bar over the C, and they C bar, and basically that's your total cost divided by how many units you produced. Again, very simple. Now, over here, these are derivatives. So if you've ever heard the term marginal revenue, marginal cost, or marginal profit, those are actually derivatives. Now this is R prime, this is C prime, and this is P prime. Let's talk about profit for a minute. If I wrote on a test that I had this scenario, I'm selling calculus textbooks, and so X is number of textbooks sold, and profit is going to be in dollars. So if I wrote this sentence right here, what would that be saying in this situation of calculus textbooks sold?
What's the right side?
The right side is dollars.
So the amount of dollars you're making is going up.
Well, now time out. P is dollars. P is profit, so that's dollars. And X, the input, is textbooks.
So your profit is increasing by 0.03 every one sold?
Okay, the key was everyone sold. Now, the reason I changed my mind when you were asked what's the right side, what would be the units on 0.03 here? Dollars per book, right? Dollars per unit, dollars per book, right? Because it's a rate, it's a derivative. So what, Zach, say that again. You said the profit is
increasing by 0.03 every one sold.
Notice I said increasing. Take back to the chart, right? If P prime is positive, it means P is increasing. This means my profit is increasing by $0.03 for each book sold at 100. It's very important you say at 100. Somebody in the other class, his first stab at it, said when you make 100 textbooks, or when you sell 100 textbooks, you're making $0.03 per book. That's not right. Everybody see why that's not right? It's only at the 100th book that your profit is increasing by that amount. That's not what you're making, it's how much your profit's increasing. Okay, so what would the business person be interested in here? Well, hopefully max profit. What should P prime be when at the max profit? 0, right? I mean, it should be at a max, which is when the derivative is 0. So business people would talk in the language of marginal profit being 0. If the marginal profit is positive, if the marginal profit is positive, that means their profit is still increasing, which means they want to keep making more books probably. But if the marginal profit is negative, it means their profit is decreasing. Maybe they're making too many. In other words, they can't sell them all. Or maybe by making more, they have to hire more people or pay overtime, right? And then now it's not profitable anymore. So they would be interested in that point, that number of books sold that would give them the maximum profit. Okay, so but that's the term. That's the terminology. Marginal cost, marginal profit is another name for the derivative of profit, derivative revenue, derivative cost. Okay, so those are some terms. When you run into them, or you won't in this first set of homework exercises, I think those first couple in the packet, but that's where you can look in the packet to remind yourself about those terms. Okay, let's go back to our textbook homework problems. And I'm going to change that assignment sheet just a tad. If you want to look at that, we're going to change that just a little bit. On 28, on problem 28, this is 4.3, day 2 now. Okay? On 28, we're only going to do parts A, B, and C. We're only going to do parts A, B, and C. Not D. Okay, so we're going to do 28, A, B, and C. And also on 21, we're only going to do part B. On 21, we're only going to do part B. Okay? All right. So I'm going to help you get started with 28B. So this is on page 241. All right, read the problem. Go ahead and read 28, and then read part B. Page 241. 241. Okay, so where are we going to start? Picture would be a great start. In 28B, we're talking about a rectangular parcel that has a square base. And then they give you a hint. They talk about that thing called the girth, and the 108, can't exceed 108, and there's a long side, right? The long side's involved, okay? So, and the hint is there's two different possibilities. Right? So, square base, so that would look something like, excuse my drawing, but something like that. I'll take it. After years and years of practice, I finally started to make something reasonable. But here my long side is that, right? I've made it so the height was my long side. Now it's supposed to have a square base, so I could call this B and B, right? But it said there are two cases to think about, right? What would be the other case? The base is the longest side instead of the height. So over here, and so we're going to have to, it's going to like two problems in one, which is great. 28's already like 3 parts, and now each of the parts is like 2 parts. But so in other words, now we would have our square base as our long side. like that. Something like that. And will that make a difference? And then, well, that's what we'll find out. Okay, that's what we'll find out. Somebody in the other class said, well, it wouldn't be a cube, you know, because one of the things we learned in problem 22, the whole point of problem 22 in yesterday's homework was, if you have a fixed perimeter, what's the max area? Well, it's a square. And then part B of 22 was, if you have a fixed area, what would minimize the cost? Well, again, it's a square. What would use the least material? Again, it'd be a square. Okay, so somebody in their class said, well, wouldn't it be a cube? Wouldn't a cube be the answer to this? Well, if we had a fixed surface area, what would be the max volume? It would be a cube. Okay, but that's not the constraint here. The constraint's not a fixed surface area. The constraint is that 108 business, right? And so I think it may make a difference. All right, so let's go back to our steps. Now we've done some labeling. We've drawn a picture. Let's go back to step 1, which was what in our list? Identify the quantity we're maximizing or minimizing. In this case, it's what? Max volume. So step 2 is write an equation for that quantity. So we need a volume of this thing. What is it? So it would be, so our thing we're trying to maximize would be that right there. Correct? That was step 2. Step 3 was what? Get in terms of one variable. Use some other information that's in the problem to get it in terms of one variable. Well, that's going to be that 108 business. So what did that say? Read that again. Long side plus the girth. And the girth is the perimeter of a cross section perpendicular to the long side. So here's the long side. Perpendicular to that would be this way. So wouldn't that be this perimeter here? Right? Isn't that the girth? Okay. So how would I write that?
H plus 4b is less than or equal to 108.
H is the long side plus the girth, which is the perimeter perpendicular to that long side. That'd be 4b. Now he said less than or equal to 108. Since we're maximizing the volume, doesn't it make sense that the max would occur if we use all 108 inches that we're allowed? So I think it would be okay to do equals 108, not less than or equal to 108. Makes substituting easier. So. Now, isn't that what you needed? Aren't we really past the hardest part now?
Yeah.
I mean, because now we can substitute, we can go in, now we got our equation, you'll get your equation in terms of one variable, you're ready to go, right? Now, you're going to have to do the same thing over here. Now, I think that equation is different over here. Because the long side is B now, right? The long side is B, so where will the girth? The long side's this way, perpendicular to that. This way, right? So the girth will be that cross section, right? So your long side will be B plus that girth equals 108. So you'll have a different equation here. Your volume, of course, will be the same. So you work this out as one problem, you'll get a max volume for that. You'll work this out, and you'll get a max volume for that, and the max will be whichever one of those two is bigger, right? But it's really like two separate problems. Find the max with these conditions, find the max with these conditions, and okay. Then part B talks about, or part C talks about a cylinder, so you do this all over again. You have two cases, okay, go. Go to work. Yes.